Okay, so Qiang got his PhD at the University of Utah, working with Professor Quonan Liao, very famous professor, and doing atmospheric radiation and working on cirrus clouds. He's been at the University of Washington since 2000. He's now a full professor at the University of Washington. He's an expert in radiative processes, radiative parameterizations and climate models, cloud aerosol radiation climate interactions on remote sensing, climate change, tremendous publication record, very strong citation, and very many things that we are interested in this audience. So he's a fellow of the AMS, the AGU, the AAAS, and he's won all kinds of interesting awards, but we're really happy to have him here visiting today. So Qiang, tell us about the Brewer-Dobson circulation. Thanks.
Yeah, thanks, Bill, for the introduction, and thanks for inviting me. And I would also like to thank, Laura, Bill, for making all the arrangement for my visit. I've been very much enjoying my meeting with all people in the, upper troposphere, lower stratosphere group. I've been meeting, I have 7 meetings, so it can be busy, but I learn a lot. So my talk today is strengthening of the Brewer-Dobson circulation since 1980, seen from satellite. So Brewer-Dobson circulation is a Lagrange mean mass circulation in the stratosphere, which consists of the meridional cell in each hemisphere, with air moving, up or across the tropical tropopause, moving forwards and sink to the actual tropics. And the Brewer and the Dobson were the first to describe this circulation in order to interpret the observed, ozone and water vapor distribution in the lower stratosphere. And we know Brewer-Dobson circulation actually plays a very important role in controlling the stratospheric ozone distribution, controlling the tropical tropopause temperature, the entry value of the water vapor going to the stratosphere from tropics, and even control the tropical tropopause layer in cirrus clouds, like I show in this figure. What I show here in the upper panel, the red color scale shows TTL thin cirrus cloud observed from calypso observation, LiDAR observation. And the cloud I define here is for all cirrus with base higher than 14.5 kilometers. Okay, and the blue curve shows 100 hectopascal temperature contour, and the arrow shows wind fields. So you can say, in terms of spatial pattern, actually both temperature at 100 hectopascal and the TTL cloud fraction, sort of controlled by the equatorial wave, like the Kelvin wave, Rossby wave. But when we talk about tropical mean, okay, what I show here, lower panel, the blue line shows 100 hectopascal temperature, average over tropic 30 to 30, and the red curve shows TTL cloud fraction from calypso LiDAR observation, and the black line shows the Brewer-Dobson circulation index. Okay, you can say, in the signal cycle, in the tropical mean sense, the 100 hectopascal temperature and the TTL cloud both, tightly, follow the Brewer-Dobson circulation changes. So this figure demonstrates, at least in the context of the climatology and the signal cycle, we can say, the bottom-up process, control the spatial pattern. But in terms of annual, signal cycle, actually the top-down Brewer-Dobson circulation control the, temperature variation and the TTL cloud fraction variation. So the age of the stratospheric air is defined as a time to transport air passing from tropical tropopause to given location. Like for example, we are talking like 40-degree, latitude at altitude 25 kilometers. The age is about 5 years. Okay, so that means the air takes about 5 years from here to here. Okay, so we can say the age of the stratospheric air is an indicator of the strength of the Brewer-Dobson circulation. By the way, please interrupt me whenever you have questions. Otherwise, my pace could be getting faster and faster. So the Brewer-Dobson circulation is considered, to be driven remotely by the planetary wave and gravity wave breaking in the extratropical, stratosphere, which acts like a suction pump, pulling the air, upward from tropics, like shown by the famous, Horton, chart. More later, study, including the most recent one, suggests actually the subtropical synoptic wave and the equatorial planetary wave also play a very important role in driving the tropical lower stratospheric upwelling. I will come back to this point later on about the mechanism. The global climate model with good representation of the stratosphere all predicts an increase in the strength of the Brewer-Dobson circulation in response to the increase of greenhouse gases and also in response to ozone depletion. Okay, so the mean stratospheric air age would be expected to decrease in last several decades because of ozone depletion and the increase of greenhouse gases. Like shown in this figure, from the GFDL model, 1960 annual mean age and the 2000 annual mean age. So you can say actually the air become younger, compared to 40 years ago. So using the I think using the NCAR model, you guys show the Brewer-Dobson circulation strengthening by about 1.2% per decade using stratospheric age as an index. And from GFDL model show about, could be as large as 0.7% per decade. Okay. What I show here is the observed long-term evolution of the mean age above, 24 kilometers altitude, observed in the Northern Hemisphere with a latitude range from about, 30 to, 55 or so, depending on the color. So the SF6 derived age value shown by the circle and the CO2 derived age by the triangle. So instead, from observation, instead of we say the decrease as predicted by model, actually we say insignificant change or even slightly increase of the age. Yeah. So I will come back to this also later on in my talk. So before that, so I first put a simple equation, approximate linearized form of the transform lowering mean thermodynamic equation. The partial T pi T is a temperature change locally equal to Q is a radiative heating rate, W star is residual velocity, and S is a stability parameters. Okay, bar mean zonal mean. Okay. So under equilibrium situation, this term would be 0. Okay, so now if we replace the radiative heating term by using the Newtonian cooling, by this equation, so this is what we have. Okay, so if we give in the composition, okay, so the TE is a radiative equilibrium temperature. If we give in the composition, the atmosphere, this will not change. Okay, so if the circulation change, like strengthening of Brewer-Dobson circulation, okay, like if W increase, you would expect this decrease. If this decrease, you would expect this increase. So that means if you have Brewer-Dobson circulation, from move up, then power down. Okay, if this is strengthening, so you would have positive W star in the tropical region, but negative in the extratropical region. Okay, so you would corresponding to this, when this increase in the tropical region, you would expect this decrease trend, but the downward strengthening, that's a elective of this, you would expect the positive in the extratropical region. So my argument here is lower stratospheric temperature could be also useful indicator of the change of the Brewer-Dobson circulation. So actually, many studies also did show that, indicates, long-term cooling trend in tropical lower stratospheric temperature may be partly associated with the increase tropical upwelling consistent with the accelerated Brewer-Dobson circulation.
So
under a climate change scenario, would you expect the thermal equilibrium, the rate of equilibrium temperature to also change?
So here, what I'm talk about the locally, partial T is 0, yeah, compared to yeah. So you sort of get an equilibrium between the the adiabatic, the balance between diabatic and adiabatic terms. I don't know if I answer your question.
I think if you go to the previous slide.
Yeah.
So PE, T sub E, the
Yeah.
radiative equilibrium
Yeah.
temperature
Oh.
is a function of the composition.
Yeah.
So that could also change.
Yeah, if composition change, yes. That's a good. Oh, yeah. Oh, okay. I'm talking. Okay. Thanks for. Okay. It's very important to clarify this. Actually, okay. So if composition does not change, this will not change. Okay, so this responds to W star change. But composition change, this would also change. So what we observed, the lower stratospheric temperature trend actually is corresponding to both this and this. So now I just say, in principle, given this would be response to this, in a sign when you have strengthening in the tropical region, you get cooling, and in the high latitude, get warming. Okay, that's respond to dynamic change. But of course, the radiative part we also need to take care of. That's very important due to change of this term. So we will come down to, how to take care of change of this part. Yeah. Thanks. Is that clear now?
I think so. We'll see. That was your question. Yeah, that was definitely my question.
Yeah. So, I mean, in the real world, actually, the change of this is due to both change of this and change of this in real world. Yeah. What I say is, conceptually, actually, I mean, at least this have signal of Brewer-Dobson circulation, although could also have other signal, but we need to take care of. Yeah. So in Engel's paper, they argue, the observed trend in the tropical lower stratospheric sphere as a tropical local phenomena. So because what the measurement they made is like the above 24 kilometers in the mid-latitude, so they consider deep cell. So this could be shallow cell. So that's the interpretation. Yeah. And then in addition, the cooling actually in the tropical region, actually if something related to the tropical upwelling, strengthening, I mean this sort of cooling signal is not really unique because the composition change due to ozone depletion and the CO2 would also contribute to the cooling. So this sort of signal is not really unique, So that's why we go to high latitude. Okay. So what I show here is the Southern Hemisphere high latitude, lower stratospheric temperature trend pattern. Actually from this paper for 79 to 2006 from the satellites, microwave sounding units, so-called the TLS channel, or sometimes also called as T4 channel. So that's the temperature in the lower stratosphere. Okay. So this is annual mean. Okay, this is for season. Okay, so what you say is that let's pay attention to the Southern Hemisphere spring. Okay, so we know in the Southern Hemisphere actually you have ozone depletion, ozone hole. So you would expect because of the composition change, you would have cooling due to composition change, the net. Okay. But if you do the mean of the high latitude, if you do the mean, actually what you get is very close to 0. Okay. I mean, I come back to the wave one pattern later on. But what I say is, in the Southern Hemisphere spring season, because of ozone hole, we would expect strong cooling due to radiation effects. But now when you do the average, what you get is very close to 0. Okay. So that means, there's something, compensate this. Okay, what's compensating actually is because of strengthening of Brewer-Dobson circulation. So they sort of show the wave one pattern is really because of the vortex actually is really not located in the pole center, but shift away. And the cooling really happens within the vortex. But Brewer-Dobson station, when you come down, it's really you can really go into the vortex because of strong vortex. You go outside of vortex. So this warming actually is related to the Brewer-Dobson circulation strengthening. This is related to the ozone cooling, but because of the wave one structure of the vortex, it's need to sort of respond differently. But one important thing is the overall, effects is about zero. So the near zero temperature trend is because of the compensation of the strong cooling, largely cancelled by the strong warming. So the idea is, the stronger Brewer-Dobson circulation would introduce faster, upwelling or high latitude, downwelling, faster. This colder, TLS in the tropics, but the warmer in the high latitudes. Okay. So now the question is how to separate the dynamics from the radiative parts. But before we do that, I want to show you the monthly trend pattern of the T4 or tropical lower stratospheric temperature and the Tom's total ozone, in last 30 years. So this two is for lower stratospheric temperature trend pattern. Okay, these two are for ozone. Okay, you say for ozone, basically you show the ozone depletion, especially strong in the Southern Hemisphere spring season. Okay, you do say slight increase. That's really because of the strengthening of Brewer-Dobson circulation. It's a dynamic. The ozone increase slightly because of the downward motion, but this is very weak actually. But overall, the composition change, related to the ozone depletion, show the decrease. So of course, the temperature you would respond to this, would be cooling trend, But here you not only say cooling trend, but you say the warming trend, like in the Southern Hemisphere, winter and the spring season. And when you do the average again, it's about zero. Okay, and actually for September, it's slightly, I would say, could be slightly positive. This is about zero. When you do the average of entire, but without the radiative part again, respond to this is lactive. So that means there must some positive part compensate this. That's because of Brewer-Dobson circulation. Yeah. So in order to separate the dynamic component from the radiative components, that's exactly the points you ask. So we use 3 months mean aldehyde flux average between 20 to 10 hectopascal. Really is not very sensitive to what we do here. For average over 40 degree forward, as an index, as a measure of the strength of Brewer-Dobson circulation. So we do this for separately for Northern Hemisphere and the Southern Hemisphere, 4 degree, northward and the southward, and then do the index, okay. And then we use, ERA-Interim data. Actually, our results are not sensitive to which data we use. So now, the dynamic components, is separated from the total observed trend, using a regression of the observed temperature on the Brewer-Dobson circulation index. So we don't sort of do the, at each grid ball, we do the regression of index, then we do the mean from the trend. So that's the dynamic components. And then the radiative components we sort of derive empirically as a difference between the total observed lower stratospheric temperature trend minus the dynamic components. Any question until now on what I'm doing? Bill? No? Okay.
Are you looking at globally everything at once? So
Yeah. Yeah, here I actually use the high latitude. I look at the I define the index for the 40-degree north and 40-degree south. So I sort of have the index for the Northern Hemisphere cell and the Southern Hemisphere cell. So instead of, if I do the two together, it would be for globally, but now I sort of do separately for each hemisphere. So for the, I do the average 40-degree north, 40-degree south. So I have index for North Hemisphere and for Southern Hemisphere for individual cell. Yeah.
I mean, since people are asking, I mean, one thing that you can question is what is the rationale for using the EP flux? I'm sorry, the EP flux, the heat flux, or the vertical component of heat flux from 40 degrees forward as an index of the VDC. I mean, they ought to be related somehow.
Yeah.
But it's not theoretically clear that there should be a one-to-one correspondence. I mean, you could try to go at it by downward control or something like that.
Yeah.
But here it's just like Newman et al. Showed that there was a correlation between these things. But it doesn't necessarily follow that the equator to pole circulation is driven only by that measure. I mean, by that eddy heat flux in that range of latitude. Right? In fact, people have distinguished between what drives the shallow branch versus the deep branch of the circulation. So, I mean, this is wrong. Just saying that
I fully agree with you. This is just one of the index. So that's why we want to check using independent. So we derive this radiative component empirically, but we derive directly. We compare what we derive here, and also we compare. So that's why we apply this to observed temperature. So we sort of what we get, for analysis, we say the observed temperature, what we derive, is makes sense or not. So instead of purely dependent on reanalysis. So I fully agree with your.
So the hypothesis is that whatever temperature change is coherent with this index is dynamically driven by temperature change. Right? And is that what you are going with this?
I mean, so now we use this index thing. We assume whatever is dynamics would be real to this.
Okay.
Yeah. Okay, so here is the example, when we apply this index, 4-degree south polewards, applied to September as an example. So this is a trend pattern in September, okay? So now when you look at the trend, close to zero, minus 0.03 Kelvin per decades, almost zero, okay? And of course we know this is have strong ozone depletion, we know radiative power is large reactive and close to zero, so we separate dynamic part. This is the dynamic part we get, okay, have positive trend, okay. Then this is the radiative part, okay, what we get, the residual between this and this is a radiative part.
Just the anomalies are in the zonal mean temperature?
This is, we're talking about here is the zona, it's the average of the entire region. In 40 degree south polewards.
So
zona mean and mean from here to here. So it's the region, the entire region mean, high latitude mean. Okay. Mean is here. So the entire mean, it's near zero. But it's really because of the dynamic part and the radiative part sort of cancel each other, but in different region, yeah. Another? Yeah. I mean, again, I consider this also sort of real because, when you have strengthening of Brewer-Dobson circulation, also bring some ozone, down outside the vortex. Yeah, but this vortex would be this side. So now we apply this to, entire this region each month. And we also apply this technique to Northern Hemisphere, 4-degree north polewards each month. Okay, then we have basically as a function of the months, for North Hemisphere high latitude and the Southern Hemisphere latitude. So that's what we get here. So that's a TLS trend, so T4 trend due to changes in the Brewer-Dobson circulation in the Southern Hemisphere high latitude. So now we talk about the average in the entire region here, And Northern Hemisphere high latitude entire this region, and the entire high latitude we just average the two together, for this period of time. Okay, so this basically is dynamic components, for the Southern Hemisphere high latitude. Okay, so that means it's about 0 in the Southern Hemisphere summer and the summer and the fall, but you get warming, start to pick up in the Southern Hemisphere winter, then biggest in the spring. Okay, so this is a dynamic component of the Northern Hemisphere high latitude. Also is average of 4-degree loss. Okay, so you can say actually you don't see much dynamic change in the Northern Hemisphere summer and the fall, but you do say strengthening. That's warming, strengthening, in the wintertime, but weakening in the springtime. Okay, and when you do the average, that's the dynamic components of the entire high latitudes. Yeah. So now so what I show here is this figure is what I get, actually the high latitude dynamic components. Okay, and like I said, using the index, using the index, the heat flux, regress, the dynamic power out, North Hemisphere, Southern Hemisphere, each month, then do the average, getting the high latitudes, okay, and the dynamic components, okay. So you can say because of high latitude, so you say the strengthening of Brewer-Dobson circulation, in this period of time, but weakening in the boreal, spring, okay. So what I show here, the red line, what I show is I didn't do anything. It just observed, lower stratospheric temperature trend, average over the tropical region, 20-degree north, 20-degree south. So I didn't do anything. Okay, so that's so you can say this, almost perfectly, sort of relatively correlated. So this gave me some confidence on the index, and also gave me some confidence on the reanalysis data I used. So that couple conclusions I can get. One thing is this is the observed, T4 temperature trend average over tropics as a function of the months. Okay. The monthly dependence, I can first claim the month dependence is basically dynamic driven. Okay, dynamic driven. Okay. And the second, because this could respond to each other pretty well, that gave me some confidence on what I did here. And when we do similar thing, I can get the radiative components here. The radiative components I show here, we can say, have very small, signal dependence. Okay, so I will come back to this later on to independently check this. Okay, so that gave me more confidence on what we get. Yeah. So now, after we separate the dynamic power from the radiative power, so the tropical annual mean, T4 or TLS trend, total, I use the lower data, okay, is minus 0.4 Kelvin per decade. The dynamic power is, minus 0.1 Kelvin per decade. The radiative power, the difference is minus 0.29, Kelvin per decade. So one result I would like to claim is our observational analysis indicate that the dynamic cooling in the tropical lower stratosphere is closely coupled with the dynamic warming in the high latitudes. By what I show the perfect relative correlation, or seesaw pattern, in the high latitude, which sort of indicates a strengthening of the hemispheric widening of Brewer-Dobson circulation. So what I say here is not really local, shallow cell, it's really deep cell. Because the warming I say is really in the polar region, which is relatively correlated with, warming in the, lower latitude. So here it shows the statistical significance of dynamic components. We derive, in the tropics. So the darker, shades mean the, 90% confidence interval, and the lighter one shows the 95. So it although not 95% confidence, but it's confident in 90%. Yeah, confident. Okay, so here what I show here is this is observed T4 trend as a function of the for each month dynamic components and radiative components. So here is for the trend average over the southern hemisphere high latitude 40 degree south polewards. Okay, this is northern hemisphere 4 degree polewards, and this is average of this I call as a high latitude trend. Okay, here is the tropical region 20 to 20. Okay, so you can like I said, the dynamic components is basically is sort of high latitude and the low latitude sort of like relatively correlated or like sort of seesaw patterns. Yeah, and for the radiative part, of course, one important thing is high latitude actually cooling is much stronger than the low latitude. But for radiative part is really, sort of have not much, signal dependence. Yeah. And this actually have dependence, but also this is larger than this. High latitude larger than low latitude, cooling. Yeah. Any question on this figure? Yeah.
Why do you have negative trend in both in the tropics and in the radiation part?
Why we have cooling in both places? Yeah.
Is it mostly ozone?
Yeah. Actually, I think my next slide would be a few slides would answer your question. What's responsible for this? So I sort of try to reproduce this using totally independent methods, using the composition. Like actually what's responsible for this, including ozone, greenhouse gases, even like the volcanic eruption, because the time period is earlier part of the period. You have because of like or Qiang or Pinatubo, you have warming. So in the first part of the 30 years, so that's what's introduced cooling. Yeah. So I will come back to this later. But this is ozone depletion. Ozone hole. Yeah, is a high latitude. Of course, whatever response for this would be also play some role here. Yeah. Okay, the study recent study by also at all also examines the Brewer-Dobson circulation trend by analyzing observed temperature, and they show they are not significant. Well, I show significant, but they show not significant. Okay, they use the Brewer-Dobson circulation index, their index, and as function of the months. So I mean, for my result would be some strengthening here, but weakening here, then strengthening here. But what they say is statistically insignificant, except this, weakening here. Okay, so I would argue the problem is because they use the index they're using the index for Brewer-Dobson circulation as a, mean temperature in the extratropical region minus temperature trend in the tropical region. Okay, so the idea is if the radiative part in the high latitude and the low latitude, they cancel each other, then you get, respond to dynamics, right? The strengthening Brewer-Dobson circulation, you get warming here, cooling here. The difference, you get, positive sign, right? But now, if the radiative part, cooling in the high latitude is larger than cooling in low latitude, so you have contamination here. So would it be mess things up? Yeah. But we know, actually, noting that the radiative cooling in the extratropics is often larger than tropics. So their study actually underestimated the Brewer-Dobson circulation strengthening trend, but overestimates the weakening trend. Yeah. So that can explain why they get different results as what we get. Okay, here just show a comparison of what we derived from the AR4 GCM. Okay, so here is observed trend in the tropics, Southern Hemisphere high latitude, and Northern Hemisphere high latitude. And I also show the radiative part, from the observation. After we separate dynamic part, we get the radiative part as a dashed line. Okay, dashed line. Okay, radial part. Okay, and the dotted line is a trend from the AR4 model. So AR4 model more or less, can similar to what our radiative part, so they don't get dynamic part. Yeah. That's expect because AR4 model, they don't consider the stratosphere dynamics well. Yeah. So here I want to show an independent check of the empirically derived radial component of the tropical temperature trend. So we show the radiative part, empirically derived independent of the months and with a value of the minus 0.29 also. So what we use is a radiation model with similarly involving fixed dynamic, heating approach. So we consider changes in ozone, water vapor, CO2, methane, and the aerosol, and so on. Yeah. Yeah.
Clarification: what you are calling the empirically derived radiative component is the difference between the observed trend and what you estimate to be the
dynamic trend. Yeah, dynamic trend. I get the radiative part. Okay, I want to compare with the.
You want to do the calculation by radiative.
Yeah, from the composition change. Yes. So this is what I get. Okay, for the greenhouse gas, actually, it's not as small as people usually expect. So actually, for the greenhouse gas, including CO2, methane, nitric oxide, and the CFC, all it's about minus 0.09. Okay, have no zone dependence. And this is ozone using Bill and the Randall Woods data set. That it's give you minus 0.15 for the T4 temperature trend. Okay, water vapor is a little bit tricky. Water vapor actually, we know the job in 2000 job. But people also sort of suggest increase, but that's not uncertain based on this, bolder data, but globally we don't know. So here, I just do the job effects, but then I don't consider the increase. Okay, this gives you positive 0.08 because 2000 job. And the stratospheric aerosol, I get minus 0.13. That's really because of the stratospheric warming due to aerosol, volcanic aerosol in the first part of the period. And SAT really mean, when you have surface warming, you have the tropospheric warming. The tail of the weighting function could really pick up some, tropospheric warming, but that's very, very small. So add all together, total radiative part is, 0.26. That's a storyline here. Okay. So we know, some of the radiative part, like the ozone, could be also respond to dynamics. So we regress out. We're using our dynamic, regress this out. But doesn't matter, if you regress without Brewer-Dobson circulation or with, the signal is about same, minus 0.25. So that's a dotted line. So that's a total, okay, based on direct, okay. And this is from our empirically derived. So you can say even the dependence on months, follow each other very well compared to this and this. So this really gives us confidence on what we derive empirically derived. And this is a vertical profile related to the ozone. You Randall Woods data, and this greenhouse gas. Okay, profile. This is water vapor, and this is tropospheric, temperature increase, since '79. Okay. And so stratospheric aerosol, we use a regression method to derive that. Any question on this part? Okay, so now, so I repeat, what we derive, total is minus 0.4, and the dynamics minus 0.11, and the radiative is minus 0.229. Okay, so now I want to convert this to the vertical velocity. In order to convert this, so I try to build up the relation between the residual temperature with temperature change in the T4. Okay, so now I use two scale of the variation. One is signal scale, using the signal scale. Okay, based on signal dependence, and one is using interannual because I don't know, the long-term trend, what's process driving this, but seasonal and interannual sort of give me some idea about what's the relationship between the two. Actually, the relation, the coefficient, they are not that different. Yeah. So I use this both to try to estimate how the cooling corresponding to vertical velocity change, and using the two coefficients. So now consider this, change, from our analysis, minus 0.11. Okay, then I use this two coefficient could be either, 0.008 or 0.005 millimeter per second per decades.
John, where does the W come from?
W is from the reanalysis. Oh no, I mean for this one is from reanalysis. It's from reanalysis, yeah, from ERA-Interim reanalysis. One is seasonal, one interannual, yeah. And here is what I want to estimate. I using the coefficient, two coefficient, using what I derived dynamic component. I want to derive the dynamic, the Brewer-Dobson circulation associated, delta W star change. So that's what we derive. When we put this into this equation using the two coefficient, we get these two value. Okay, then we, divided by the mean value, of the, so that's a vertical velocity at 70 hectopascal. Okay, we get, either 2.7 or 1.7%. The mean is about 2.2%. It's very much agree with what you guys, 2% or so. So we also do this detailed statistical analysis. So at 95% of common interval ranges from minus 0.1 to 5% is not significant, but 90% would be 0.2% to 4.7%. Yeah, I don't want to give detail about statistical analysis. So now for the comparison of the simulated Brewer-Dobson circulation changes with our observed, analysis, we use residual velocity at 70 hectopascal average over the tropics for the same period of time from 11, CCM, VAR2 model. So the mean actual relative change from this is 2%, and with a range about minus 0.1 to 6%. This very much agree with what we derived. So this is from the model, okay, from the CCM, VAR2, and this is from our observation mean value.
I have a question on that.
The
previous slide.
Yeah.
You have two values for C.
Yeah.
0.069
Yeah.
and 0.044.
Yeah.
And one presumably applies for interannual and one
Seasonal.
Seasonal.
Yeah.
Of course, they shouldn't be the same because for interannual
Yeah.
you can probably
QBO.
DDT, for seasonal you cannot.
Yeah.
So which one do you use to get those estimates?
So I use both. Because I don't know on the train, I don't know which wave process play role driving the circulation change. So I use both coefficients. I get two number. Yeah. So the two number is 2.7 and 1.7.
Okay.
So the mean is 2.2. Yeah. So now, I do I don't have time to give detail, but I do the partitioning, of the, so here's dynamic components, okay, in the tropical, related to the tropical lower stratospheric temperature change, okay. Like, it's not significant in the 95% interval, but significant in 20% interval. I do the partitioning in the Northern Hemisphere cell and the Southern Hemisphere cell, okay. So in the Northern Hemisphere cell, basically is insignificant, and most of this is contributed by the Southern Hemisphere cell. Yeah. So that's why I sort of say, we don't expect you can measure the Brewer-Dobson circulation strengthening in the Northern Hemisphere in the deep, because the strengthening in the winter and the weakening in the spring, so they cancel each other. So the annual mean is insignificant, okay? So even in the age, you don't measure the significant increase, it's not inconsistent with the strengthening of Brewer-Dobson circulation overall, because this really happened, mainly in the Southern Hemisphere. Yeah, of course, there are some other issues related to how to interpret the age, the nonlinear effects and all other things, but so the strengthening of the total Brewer-Dobson circulation is not inconsistent with an unchanged age air in the Northern Hemisphere and midlatitude stratosphere due to only small statistically insignificant annual mean change in the, yeah. And the increase, or another thing is point is that the increase in tropical lower stratospheric upward motion in the last 3 decades is a global phenomenon based on our analysis, okay, associated with hemispheric wide, Brewer-Dobson circulation strengthening instead of tropical local phenomena as suggested by their study. So conclusion is, our observational analysis indicated that dynamic cooling in the tropical lower stratospheric is closely coupled with the dynamic warming in the high latitudes, 40 degree polewards. And dynamic cooling in tropical lower stratosphere indicates the strengthening of Brewer-Dobson circulation in the last 3 decades at 90% confident level. Okay, it's not 95% confident level. And the partitioning of the tropical lower stratospheric temperature trend into dynamic and radiative part is validated using a radiation model with observed changes in the atmospheric composition. And our observation analysis indicates the Brewer-Dobson circulation strengthening by, the average, 2.2%, supporting the GCM simulation. Yeah. So next, I want to use a few minutes to sort of talk about some challenges. Yeah. Okay, first, what drives the change of the tropical upwelling in the lower stratosphere? All of the modeling theoretical analysis sort of suggests the response of the strengthening of Brewer-Dobson circulation to the CO2 increase, ozone depletion, seem to be at least related to the CO2 increase is really related to the sort of subtropical synoptic wave, like the jets strengthening, move upwards. You have more wave, in the subtropical going upwards. So it's more related to the shallow wave. Okay, it's more related to the shallow wave. That's exactly what we say in our analysis. We sort of, talk about the mass flux, related to the Brewer-Dobson circulation upward region, so we step into shallow and deep cell. Okay, the shallow cell means the Brewer-Dobson circulation, passing through 70 hectopascal, but come back, below 30 hectopascal. The deep cell is the Brewer-Dobson circulation, passing 70 and go all the way passing, 30, hectopascal, and the total is like the two, add together. So you can say the total change is really because of shallow cell. But the deep cell is very small, only maybe 25% of the total. So it's sort of consistent with what people all suggest. This strengthening is really related to the shallow cell. Okay, but
remind me, what are these estimates based upon? Is this from
this is from model from the 11 CCM VAR2 model.
This will get something like that with WAC.
Yeah.
A lot of the acceleration has to do with the shallow.
Shallow cell. It's related to the subtropical wave-driven process, and but what we say is really, it's related to the sort of entire, hemispheric, wide, Brewer-Dobson circulation, go all the way to the high latitudes. Yeah. So this is something I don't understand. Yeah. Another thing is like the signal dependence. Signal dependence. So here I say the dynamic components in the tropical region, and it's partitioning between Northern Hemisphere cell and the Southern Hemisphere. So that means the cooling being strengthening. Okay. So now in the Southern Hemisphere, for example, we say strong strengthening in the spring season, and also strong, strengthening in the winter season, Southern Hemisphere winter season, but you don't have any in another 2 seasons. But for Northern Hemisphere cell partitioning is, you really say the strengthening in the DGF season and weakening this, but not here and very small here. So total strengthening basically for Brewer-Dobson circulation, it's in the SON season is from the Southern Hemisphere, and the JGA season from Southern Hemisphere. Then DGF is from Northern Hemisphere. This from Northern Hemisphere. Yeah.
This is a trend in the tropics.
In the tropics, yeah. The trend in the tropics, yeah. But then when we go to model, I just give an example of model. Actually, the model actually behave very similarly. I mean, pay attention to the light color. For a trend in the 1960 to 2004. I forget about dark color. Okay, this is a tropical change. This you can consider as a Northern Hemisphere partitioning and Southern Hemisphere cell partitioning. Of course, the positive means strengthening. Okay, I mean, we sort of, like, for example, we go to the Southern Hemisphere first. So you can say the strengthening really mainly happens in the DGF season. Okay, but here we say zero. We say zero. Okay, so the season and this is very weak. We say strong, and this is reasonably large, and we have so reasonably large. And here is strong, and we say zero. Trends. Yeah. So the point is the signal, dependence of the Brewer-Dobson circulation. Actually, the model tend to give you the strongest strengthening in the DGF season, but the model tend to give you the strengthening mainly in the SON season. Yeah. So that's sort of another sort of inconsistency between model and yeah. Yeah, maybe I stop here. I think leave some time for question before. Yeah.
We haven't been using a microphone, so I'm not going to use a microphone.
Yeah.
We're good. So I got a question. I'm going to start off.
Yeah.
So you showed that net forcing from the Northern Hemisphere and from the Southern Hemisphere much bigger than the Southern Hemisphere
Yeah.
for that 80 since 1980 to early 2000.
Yeah.
So why do you think it's bigger in the Southern Hemisphere than the Northern Hemisphere?
You mean the dynamic part,
Yeah,
right?
the dynamic forcing. Or any idea?
Yeah, that's a good question. So I would say that's related to related to the ozone depletion. Yeah, I mean the model seems to be, I think, still have difficulty to sort of simulate the right time for the vortex breaking. I think.
It's from your observations.
Yeah, from observation, yes. So my data show like the strengthening really happen.
There's another figure you showed.
Is better.
This one.
Yeah. Oh, yeah. I mean, here, Northern Hemisphere, because of the strengthening in the winter, but the weakening in the spring, they cancel each other, so make the annual mean insignificant. But here, actually, the contribution is really mainly from the, Southern Hemisphere winter and the spring season. Yeah.
So question, so why would the circulation be increasing more in the Southern Hemisphere than the Northern Hemisphere?
So I would say,
Climate change.
yeah, I would say it's response to ozone depletion. Respond to ozone depletion. Yeah.
For whatever it is worth, in WAP, there is an increase in the divergence of activity flux during the ozone hole development period in the Southern Hemisphere. And you do get a stronger circulation in the Southern Hemisphere. So that's one model. I don't know what other models will say.
During or
Yeah.
after?
As the ozone hole develops,
Yeah.
you have a concurrent trend in the delta F, and therefore a trend in the
So would that be in summertime? After the
not on this, well, unfortunately, what I remember from the world
It may be summer, yeah.
was sort of a long-term trend, not broken down into seasons. So I don't know where most of that is coming. I would think it's coming from the
Summer.
transition season, when the ozone
I think,
hole
Mark,
has an important
you
effect.
calculated this, right?
In our reanalysis studies, we saw that big trends in the AP class divergence in DJS in the Southern Hemisphere, likely related to this ozone depletion. So by the end of the vortex,
So in
Yeah.
Southern Hemisphere,
yes, so
So-
with ozone depletion, we have less
Yeah.
cooling, so the vortex is
Yeah, that's very interesting. I think you say it's from the analysis. So that's sort of, actually, I'm on my way fly here. I'm sort of reading the paper, because I think you sent the paper. I sort of read the reanalysis paper. I still haven't finished yet. But I noticed from abstract, it's inconsistent with what we get in terms of the signal dependence. I think you sort of mentioned it's, I have to read I haven't finished yet. I mean, you talk about from reanalysis, the strengthening really happened in the, from analysis, actually, what we say is really mainly from the spring. The DGF is almost zero. DGF is almost zero, the dynamic part. It's mainly from the...
That's not what you showed.
That's... let me see, what's the best figure for that, the signal dependence. I can use, this one is fine. Yeah. I mean, this dynamic part related to the Southern Hemisphere, like December, January, February, actually become very small. It's really happen here. Yeah, it really happened here.
Yeah, so what we look at are three different estimates of the W star from three reanalysis.
Yeah.
And there's a lot of spread, but basically we feature in the dynamic reanalysis or an estimate, the one based on momentum balance. They all show in the three reanalysis the DJF clear acceleration there in the Southern Hemisphere in DJF.
Yeah, I think that's, I think we can talk about tomorrow morning in more detail. But I think one thing is very interesting. I would say, I mean, the dynamic, I mean, that of course is a total, dynamic part, from high latitude, including both Northern Hemisphere and Southern Hemisphere. I mean, what I have here, I mean, here I didn't do anything. I just using the tropical mean observed temperature trend. I mean, this, you can say almost is a mirror. It's always a mirror. So this sort of gave me confidence on what here, yeah. So that's why we sort of do different things to look at the problem, because we don't have perfect data. I mean, the analysis is not something we could trust, because our trend is based on 8 heat flux as an index, one of index defined on analysis.
Well, I would say that your estimate, P prime, T prime, would not be very useful when the winds are easterly. So if, in the Southern Hemisphere in DJF, if the vortex has already break down at some levels, like about, I don't know, 20 hectopascals. So, I mean, that would be very useful to, I mean, that Rossby waves wouldn't get that high, and maybe it's not a good estimate of the Brewer-Dobson situation in that season.
Yeah, then we would say some sort of deviation, then we would say some problem or happen consequence here. And we also try the 8 heat flux sort of simply, going passing through 100 hectopascal, similar results. I mean, we saw in this analysis, we saw the average between 10 and 50 hectopascal average, but we can also do whatever passing, 150, same thing.
I'm going to suggest we take these details and we'll look at the plots on the table or something tomorrow. Any other questions?
Well, just one observation. You commented on the Engel results. Those results, as regards change in age of air, show essentially no change. Are not quite consistent with what it was like WACOM will compute for the particular range of altitudes and latitudes where their data came from. It will compute the decrease in age of air in WACOM.
Okay.
Now, the trend that is small enough in WACOM that everything falls in each other's error bars. So you couldn't distinguish the trend in WACOM from the essentially zero trend in the Engel et al. Data. So that's one thing that is true, and why these things have been ambiguous. I mean, I think all models are predicting an increase in the Brewer-Dobson circulation. And it's pretty clear that a lot of that has to do with the
subtropical
shallow range.
Yeah, subtropical stuff, yes.
So I think the challenge here is,
Yeah.
I mean, the models compute something,
Yeah.
and there's a certain methodology for attribution in models, which is usually based on transform Eulerian mean momentum
Yeah.
analysis. And one wonders if one could do that with the data.
Yeah.
You know, essentially cast this analysis that you look on data in the same framework
Yeah.
as the transform Eulerian momentum analysis
Yeah.
on the
Yeah.
model, where you will get a closer correspondence that
Yeah.
you can compare more exactly.
Yeah, yeah,
Because, I mean, there's no theoretical basis,
yeah, yeah,
precise theoretical basis to associate changes in the circulation with just B prime over
Yeah.
a certain range of latitude,
yeah, yeah,
right?
yeah,
I mean, there's reason why it ought to be so and why they ought to be correlated, but there is not, it's not a rigorous one-to-one correspondence. Right?
yeah, yeah, I agree.
So maybe that's one way in which one could make progress, by trying to see if one could do with the data an analysis similar to what people do with the models.
Yeah. Yeah, I think one challenge is, you know, the data we don't have. The model, you can have anything you need, right?
Yeah.
The model can provide you, but data, I mean, there's some issues. The data, you know, I mean, the homogeneity of data, or some data is not available, or, you know, so that's why for long-term trend is very challenging. You always can challenge one way or another, you know. I mean,
if gravity waves, for example, have played a major role, I don't see how you're going to get that result.
Exactly. That will be you know, yeah. But still, I think, you know, we have sort of reasonable confidence, because, I mean, when I said this figure, I said, okay, that's still reasonable. And when I say, you know, the radiative part we derive from observation will also tell you similar story and have independent with the 6 months, that's gave me more confidence. So we sort of try to look at the problem from different angles, really give us more confidence. That's the only thing we can do. You know, in terms of long-term data, so we couldn't rely on one data, you know. I mean, you always can shoot me down by chance, say, okay, I don't believe, you know, one thing, you know, you have some problem. You know, I mean,
Well, there's a fair degree of internal consistency.
Yeah, exactly.
Here. I mean, you would expect the trends in tropics and high latitudes
Yeah.
to compensate each other
Yeah.
were due to a change in circulation.
Yeah.
And the fact that when you take the trends and you
Yeah.
estimate the relative trend that
Yeah.
agrees with the calculation is also something that gives.
Yeah, yeah.
So the question is in the details now. I mean, for example, why the models show the biggest trend in September, October, November,
Yeah.
or rather December, the velocity data show
Yeah.
January, February.
Yeah.
So
Yeah.
that needs to be understood, and perhaps if you can cast the analysis of the data in a way more similar to the way the models have been analyzed,
Yeah.
perhaps, you know, you can get at the reason for these discrepancies.
Yeah.
Okay, let's thank Qiang again.
Yeah, thanks.